Hi everyone, so in this video we will focus on discussing rectified linear unit hidden layer activation that are known as Relu, and basically they are very common and in state-of-the-art deep learning algorithms, so they are worth discussing, and also the variants of Relu. So Relu is basically applying element by element. So if you have a 10-dimensional vector and then you apply a Relu unit, element by element, it passes the positive values, the positive elements unaltered, and the negative ones become 0. Now, the linear part, which is the active region part, is good to have linear behavior in hidden units because it helps make the gradient consistent, it has a consistent direction, and it doesn't saturate. Now, the intuition behind the negative part is that we discussed in the last video is sparsity seems to be a really crucial feature of hidden layer activation functions. However, when you have the negative side equal to 0, this is also a saturation region, right? So that's not a problem if you're already close to the optimal solution or to a good solution, but it becomes a problem especially at initialization. So with Relu, usually the bias value is initialized to a small positive value so that the unit becomes active in the first training iterations. And in the first few training iterations. And the reason is that you want more flexibility at the start of learning, right? So the saturation region, or the exact 0 for the negative side, makes things sometimes hard when training because a unit might not have a chance to be active and learn during training. So here the gradient would be equal to 0, so no learning happens if you are in the inactive region. So this is the reason behind, basically, or this is the motivation behind the variant family of Relu units. And this variant family is defined by adding a parameter or a factor alpha I times the minimum of 0 and zi. So here the maximum of 0 and zi, this is the same as the active region here, the linear part. But then in the negative part, you add the value of the input times the value of alpha I, times a parameter alpha I. Now, if alpha I is a very small value, then this is called Leaky Relu. And the idea is to give a hope of that unit to go into activation again. So it basically enables learning, but at the same time it's a very small value, so it will, like in terms of inference, it's as if this unit is inactive. It will have a negligible contribution to further layers. Another variant is alpha I equal -1. This is called absolute value Relu. And basically absolute value Relu looks like this, right? So you have the absolute value of the input, that's what you take. Now, this is useful for object recognition in images under different illuminations, for example, right? So if sometimes the positive and negative values can refer to different illuminations, but the same object or the same semantics in the picture. So this is usually useful in object recognition in images where polarity reversal of the illumination should not matter. So again, just this example of object recognition gives you an idea that sometimes these choices are governed by the nature of the application, not just by the optimization and computation and generalization features that we usually discuss. Now, the third variant is having alpha I as a learnable parameter. So it becomes part, like the weights and biases, it becomes parts of the set of parameters that you are learning according to the gradient of the cost function. So basically we'll compute the gradient with respect to that parameter as well and update that parameter to minimize the cost. Now let's see the advantages and disadvantages of doing this. So obviously when alpha I is a learnable parameter, this adds flexibility in learning, as more functions can be possible to learn, right? So the same network sometimes can have absolute value Relu by setting the alpha I equal -1, sometimes can have leaky Relu, sometimes it may have another third option. The disadvantages is basically it adds a burden in computation, because this is more gradient computations, more parameter updates. And it can also lead to overfitting. What we mean by this is it can lead to customizing the solution too much to the training data. So the choice of alpha I can be custom tailored to the training data and not transfer or not perform well with the test data. Now, just to show you an idea of how complex these arguments can go. So typically you can think of making something more like a learnable parameter instead of fixing it as doing overfitting. But it can also lead to underfitting, because when I make the model more complex, I need more time to learn, right? So if I don't have the computational resources to fine-tune that very complex model, then I can come up with something that doesn't even fit the training data, right? So this is usually a discussion that we will typically have when discussing complexity. Is increasing complexity adding more to computation or no, right? Is increasing complexity resulting in overfitting or underfitting? These questions, the problem with them is that there is really like you have to consider the computational resources, right? So all the factors play in simultaneously, and you have to consider the complexity of the learning problem itself. So with limited computational resources, complexity of the hypothesis space can actually lead to underfitting, right? But if you have unlimited computational resources, or if the computational resources are enough, then it's expected to lead to overfitting. And the same thing. So it also, the same thing with computation. Typically, having something more learnable, right, will require more computation. But maybe actually, when you fix the choice of the parameter, because that choice is not correct, maybe it leads to unstable optimization, which will lead to more computation, more training iterations until we reach the final solution. Maybe by making it learnable, you reach the solution faster, right? So even when we say that complexity requires more computation, that's also typically, but in some cases it might actually reduce the computation if the right choice of the parameter is really very dynamic, meaning that it can change from one data set to another, and fixing it will make the optimization much more difficult, because you have to find that same solution for the different settings. Now, the last variant that I want to discuss, and next video we will focus on it more, is what's called max out. And max out is basically taking the maximum of an input set of parameters. So let's say this is the layer before the max out activation. Then basically I connect a set of nodes to each max out unit, and that unit will output the max. Now next time we'll discuss in detail why are we saying that this is a variant of Relu, what's the relationship between max out and Relu, and what are the advantages and disadvantages of using max out activations. Thank you.